Hi and welcome to video 6 on this series for Unit 4 Topic 1 Integration. This is the Applications Integration Volumes of Revolution, and we are now talking about rotations around the y-axis. So let's talk about how we determine the volume of a rotation around the y-axis. First of all, what is the area bounded by the function y equals x squared, the y-axis, and the terminals y equals 0 and y equals 4? Now, interestingly, if we highlight here the x terminals 0 and 2, we could, of course, determine, so this is solution number 1, the integral between 2 and 0 of x squared dx, and that, of course, would be 1/3 x cubed between 2 and 0, which would be 2 cubed is 8, 8 thirds minus 0, 8 thirds. Units, we're not cubed anymore, squared. And of course this would be the area underneath, so we would do, therefore the area shaded would be equal to the total area, 4 times 2 minus 8 thirds. A little bit ahead of myself there. And 4 times 2 is 8, which is 24 thirds minus 8 thirds, 16 thirds units squared. There's method 1. Method 1 is pretty quick, maybe even quicker in this case, but I want to show you method 2 because it gives us the indication on how to do volumes of revolution around the y-axis. And you know what? Sometimes it would actually be quicker in this case. So method 2 is to actually integrate around the y-axis. So we're going to integrate between 4 and 0 and the function, so we're actually integrating x dy. You see the key here is that over here we're integrating y with respect to x. Now we're integrating x with respect to y. And so this is equal to the integral between 4 and 0 of y to the power of a half. Because of course that function becomes x equals the square root of y, which is y to the power of a half to y. And that is equal to y to the power of 3 over 2 divided by 3 over 2 between 4 and 0, which is equal to 2 thirds y to the power of 3 over 2 between 4 and 0. And the 0 just cancel out. We get 2 thirds times 4 to the power of 3 over 2. And 4 to the power of 3 over 2 is the square root of 4 to the power of 3, which is 2 to the power of 3 is 8. 8 times 2 thirds is equal to 16 thirds. And voila and woohoo, there we are. We have a solution. So this is a really nice way of looking at two ways of doing this area that are slightly different. Arguably, if all you had to do was this area, well, this way does work really nicely and you probably wouldn't bother learning a new way. But we need this new way now in determining rotations around the y-axis. Because we're going to rotate around the y-axis, we cannot just calculate the rotation around the x-axis and subtract, because that will give us a whole different shape. So we can determine areas between the functions and the y-axis, and we can determine volumes of revolution of functions rotated around the y-axis. The x-axis was, the volume was pi times the square root of b between b and a of y squared dx, and then we just work out what y was, substitute in it in terms of x, and square it. The y-axis is exactly the same, except we have x squared dy. And that makes sense, doesn't it? So let's have a look at some examples. Example 3 is a fairly simple one, because to find the volume of revolution formed when this is rotated around the y-axis between 2 and 4, we just do the integral between 4 and 2, the upper bound first, of x squared dy with a pi in, of course, and that's our volume. And I'll just move this to the side so I can see it. And of course, x squared, hopefully you can see, is just equal to y minus 2. You don't have to rearrange it to find x and then square it back out. So be really careful that you don't overdo the question. We have x squared already. So the v is equal to pi between 4 and 2 of y minus 2 dy, which is equal to pi of y squared over 2 minus 2y between 4 and 2. And that's equal to pi times 4 squared over 2 minus 2 times 4 minus 2 squared over 2 minus 2 times 2. And if we calculate this, 4 squared over 2 is 8. 8 minus 8 is 0. Minus 2 squared over 2 is 4 over 2 is 2. Minus 4 is negative 2, but negative of that, and this comes out as 2 pi. So the solution here is 2 pi units cubed. So there you have it, the volume of revolution formed when that function is rotated around the y-axis between 2 and 4. And we should always do a little bit of pre-checking that this function exists above or below the y-axis or the x-axis appropriately. But if you have a look at this function, it works perfectly well because the function itself looks like this. And we'll get this side as well. But between 2 and 4, we have this bit here. So it's this shaded region rotated around. Even if we include this side, which we could do, when you rotate it around, it's still the same shape. And now let's have a look at example 4. A fruit bowl of volume 12 pi cubic units is designed by rotating the function y equals 1/4 x squared in the first quadrant from y equals 0 to y equals a, where a is greater than 0, around the y-axis, determine the value of a. Okay, so let's first of all get our heads around this question by drawing an idea of the function. 1/4 x squared will look like this. A quarter, remember, is a dilation. It is a vertical dilation that flattens it out, which kind of makes sense. We like our fruit bowls to be nice and flat. This is our y-axis. This is our x-axis. Now, this is 1/4 x squared in the first quadrant. It's from y equals 0 to y equals a. Actually, I'll put a up here somewhere. A is there. A is the point. So when you rotate it around, the volume is 12p cubic units. So what we're going to do is determine the integral, the volume, is equal to pi between a and 0 of x squared dy, and we want that to be equal to 12 pi. So I'm going to run through this now, but first of all, let's divide through by pi, shall we? That's worked out nicely. Bam. The integral between this a looks like a 9. A and 0, x squared, hopefully you agree, x squared equals 4y. 4y dy equals 12. So therefore we get the integral of, substitute in 2y squared, a to 0 has to equal 12. And so we get 2a squared minus 0 equals 12. A squared equals 6, and a is equal to the square root of 6. And a is just a unit, it's just the height of the bowl. So the bowl has a height of the square root of 6, whatever that is, whatever it's measured in. It's actually a really shallow fruit bowl, it turned out. Anyway, that doesn't matter. This question is done, and we're happy with this question. And that's the way it works out. Now, example 3 and 4, you'll notice that the functions we used were quite simple functions. And it does seem to happen a bit because we're testing your volumes of revolution around the y-axis, but I could have made them harder functions. Instead, what I chose to do is do a question as a second example that was complex familiar, but for a different reason, for the fact we knew the volume but not the upper bound. All the best.